This is problem 16 of the QHack 2023 Quantum Coding Challenges, and this one is entitled Secrets in Spacetime. Now what we're told is that in this problem, someone wants to generate a quantum state, and to do so, they're going to use the first half of this circuit. So it consists of a Hadamard gate on qubit 0 and some control rotation gates with an angle of theta. And then after preparing the state, they want to send it to someone. But they don't want that state to be intercepted. So they want to encode it using the following circuit that consists of RZ and RX gates with some angles of alpha and beta. So the idea here is that only the person that is intended to receive it, who will also have those angles, could apply the transpose conjugate of this encoding operator to decode the state. The issue is that we're told that for some angles alpha and beta that are given to us, there could be a state at this point that doesn't get encoded by this operator, or the encoding is not very secure, meaning that the resulting state might be too similar to the input state. And the way we're going to evaluate if the values of alpha and beta are secure enough is by computing this expression that is given to us and checking if it's greater or equal than 1 minus epsilon, where epsilon is a parameter that is given to us. Now, to understand this problem, we need to take a close look at this equation and see what it means, right? So if we see here in the rightmost part of the equation, we have the operator u of theta applied to the all zero state, which basically this is just the state at the output of this circuit. And then on the other side of the equation, we just have the transpose conjugate of that. And then in the middle, we have the unitary operator of this encoding circuit. So basically, this equation seems to imply that what we're calculating here is the expectation value of the state that we're preparing with respect to this operator that is the unitary corresponding to this encoding circuit. Now, for this problem, we're told that we have the freedom to solve it however we want. So we could basically just compute this expression analytically and see if for a given value of alpha and beta, there are some values of theta for which this expression doesn't hold. But given the way this equation looks like, we can say, well, here what we're doing is we're calculating the expectation value of measuring a state with respect to some operator O, right? So the way we do that is by computing the sandwich product here of that operator with respect to the state psi, which in this particular case, that psi is just basically the unitary u that we're using to prepare that state applied to the all zero state, and that gives us this expression here. And for this particular problem, well, this operator O is just basically the unitary of those rotation gates applied to both qubits, right? So it is very tempting to just basically create a Q node in pennylane for a quantum circuit that generates the state at the output using this unitary u of theta and return the expectation value with respect to this operator that we have here in the middle, right? So that seems like a reasonable thing to do. And then just sweep the values of theta and see if for any of those values, this whole expression is greater or equal than 1 minus epsilon, right? And if there's some value of theta that meets this condition, that means that the alpha and beta that are given to us are not safe. So let's go ahead and do that and see what we get. So the first thing we do, as always, is we import pennylane as QML and NumPy. And then what we're going to do here is just define a function. We're going to call it u psi that generates that state of interest. So it applies the Hadamard gate and those control Rx and Rz gates. So that's just this circuit right here. And then we're going to define a function. We're going to call it isUnsafe. And we're going to pass the values of alpha, beta, and epsilon that are given to us in this problem. And as we mentioned, we're going to create our Q node by first defining our device. And the Q node basically just calls the function that prepares the state of interest, and then it's just going to return the expectation value of that observable we discussed, which is the unitary of that encoding operator. So here we basically are passing the Rx gates applied to wire 0 and 1, and the RZ gate applies to wire 0 and 1, just like shown in this encoding circuit, and then calculating the expectation value of the prepared state with respect to that operator. And then what we're going to do next inside this function is just define an array with all the angles, so basically from minus pi to pi, with some small step size. Let's do 0.1 for now. And then we're just going to pass each of those angles to our function and check if the absolute value squared of that expectation value is greater or equal than 1 minus epsilon. And return true if that's the case. Otherwise, return false. Okay, so here now what we're going to do is copy and paste different inputs for alpha, beta, and epsilon to check if this is working correctly. And here I have the expected outputs for each of these inputs. So if we start with this input 0, what we see is that we get the correct answer, so true, but we also get a warning here. And this warning is telling us that the operator that we're using to calculate this expectation value is not Hermitian. So in pennylane, this expval function expects an observable, so basically a Hermitian operator, which in other words has real eigenvalues. So when calculating this expectation value, if we're getting a complex value instead of a real number, what's happening is that the imaginary part is getting ignored. And the reason for this is because this circuit right here is not necessarily Hermitian, right? So we could say, okay, well, that's fine. We got the right answer. So let's see what happens for the other inputs. So for the second one, we now get the correct answer again. For the third one, we get the incorrect value. So that means that this approach definitely doesn't work, right? And that's just because pennylane expects Hermitian operators to calculate expectation values. So you can't compute complex numbers here. So what else can we do to solve this problem? Well, another approach is to just basically go ahead and do something very similar, but instead of using a circuit, just get the matrices for the unitary that prepares the state, the transpose conjugate of that, and then also the matrix for the operator that we have here in the middle, of which we want to calculate an expectation value with respect to. So let's go ahead and do that. So we can now define again a function. Now let's call it isUnsafe2. And the first thing we're going to do is define that operator that is basically the same thing we were passing here to this expval function. So I'm just going to copy and paste that. But we want to calculate the matrix. So we can use this QML matrix function to do so. And then since we're doing this by multiplying matrices, I need to also create the ket and bra versions of this state vectors, or the all zero state, right? So I can do that by just defining an numpy array for that, which represents the all zero state. And then the ket is just basically the transpose of the bra. I don't need to take the conjugate of it because all values are real, right? And then I'm going to do exactly the same thing I did up here, just define the angles and iterate through them, and then compute the unitary of the state preparation circuit, so this u of theta here, by just basically using this QML matrix function and passing this uPsi function that we had already defined up here. So I can do that by passing that to QML matrix, and then this returns a function that needs to be evaluated for each theta. And then I can do the same thing for the transpose conjugate of that. So let's call it U dagger, where now I'm going to use this QML adjoint on that U psi function I already defined. And then we can calculate the expectation value just by doing the matrix multiplication of all those components. So the brow of 0, U dagger, the operator of this encoding circuit, which I call O, then U of theta, and the ket of 0, right? And then just like I did above, we're just going to check if the absolute value squared of that expectation value is larger or equal than 1 minus epsilon, and then return true if that's the case. If not, return false. Okay, and now let's go here and copy and paste the same inputs we were using before, but now let's evaluate them using this unsafe2 function. And here we can see that if we evaluate that input 0, we get true. Input 1, we get false as expected. Input 2, we get false, and that's because I need to make sure that I go over all the values of theta. So let's just reevaluate that. And here we see true. Okay, let's do it again. So for input 0, we get true. Input 1, we get false. Input 2, we get true. Input 3, we get true. So now we have a correct solution to this problem. Now, just to show you the difference between what we're computing here, which includes the expectation value of an operator that might not be Hermitian, with respect to what we did here using the Q node, which was ignoring the imaginary part of that, I just created a function that compares the two solutions and just plots it for us. So here I'm doing exactly the same I did before, but I'm just plotting what we would get for the circuit and what we get with this equation that gave us the correct answer. And then here I'm drawing the value of epsilon. So this is for that input 2. So here you can see I'm using input 2. And we can see why in the case of the circuit it was failing, because it's only giving us the real part of the solution, whereas now here on the equation we're computing the complete complex value number, then taking the absolute value squared of that, and that's what's being plotted here. So if I do here input 0, then we can see that both of them were passing because the epsilon was below, the 1 minus epsilon was below both of them. Same for input 1. Both of them were below that 1 minus epsilon, so they were both passing, right? They were getting the correct answer. But in the case of input 2, that's where, in the case of the equation, we get that the solution is not safe, whereas for the circuit, it's telling us it is safe.